So hi everyone. This is the NASA Exoplanet Archive. It is a big database that holds all information on all of the currently confirmed exoplanets, and this thing is updated daily. So if there's any information or updated demographics or new systems you're interested in, this is the place to look. Um, so I guess we have 30 minutes. Okay.
20, 30 minutes. Yep.
20, 30 minutes. Okay. Yeah, so let's just take some time to step through all the different data products available here and some of the website's utility. So to start, you'll see that there's this running counter of different types of confirmed exoplanets. So these are confirmed confirmed planets. Individually, there's a subset of test confirmed planets, as well as project candidates. Um, so if you guys have already talked a bit about exoplanet detection methods, you might know a little bit about TESS. It's the Transiting Exoplanet Survey Satellite, one of the biggest workhorses in exoplanet detection currently, monitoring the sky and looking for transit signals for periodic dimmings. But the transit itself is not necessarily a confirmation that a planet is there. So once TESS's pipelines pick up some kind of periodic dimming signal, we require some follow-up observations, usually from the ground, through spectroscopy or photometry, to confirm that the planetary signal is indeed real. So there's a bunch of candidates that need confirmation, and often we look to these candidates to plan our own observations and decide what we want to pursue using the resource we have on the ground. Um, and then I guess while we're here, so this is popping up right now. Let's look at some of the pre-generated plots on the Exoplanet Archive. So almost every exoplanet talk you go to might have one of these plots in the intro, because it's a good way to just visualize the distribution of confirmed exoplanets these days. So this is the mass versus orbital period diagram with the points kind of coded by shape and color. You'll notice that a lot of these points are purple and green, which are transit method and rate of velocity method. So these are by and large the most common detection methods. But then we have all of these other options that are also kind of beginning to fill out different parameter spaces on this mass versus orbital period diagram. A lot of the transiting planets are short period because we are better able to detect shorter period planets. Their transit depths are a little deeper and their transit probabilities are higher. For radial velocity planets, we're able to detect typically more massive planets because their radial velocity influence is larger. For imaging planets, we can only look at very massive and very distant companions because the contrast between planets and stars is quite large to get in visual, just like direct imaging. Um, and yeah, that's kind of that. You'll notice that also we kind of have no discovered exoplanets that are exactly like the ones in our solar system. So these bright pink points are our solar system planets.
Hmm.
Sorry? Never mind. So yeah, currently we are working on, sort of some new instruments or missions to push our detection limits to lower masses, to longer periods, and try to see if it's real that our solar system is extremely unique, which is not likely the case, or that we're just not able to detect things at these sensitivities, which is more likely. Okay. Does anyone have any questions so far? We should leave questions to the end. Maybe to the end. Okay. Um, Here is another kind of interesting plot we can look at. It's the number of exoplanets discovered as a function of year. So our first ever exoplanet was discovered back here in 95, I believe. I don't, it looks like it's a little before. With 51 Peg B. It was a radial velocity planet, a hot Jupiter planet. And since then, for about 10 years, radial velocity was the main method to detect exoplanets. However, with the onset of someone's sneezing.
Yeah, I muted them. Please mute them.
Okay.
Please mute
Okay.
yourself, everyone. Mute.
All right. And then with the launch of Kepler and test missions in the 2010s, transit starts to take over as like the main workhorse for detecting exoplanets. With was this the launch of Kepler? Yeah. Um, I guess that's kind of it for that. And yeah, basically we have a bunch of different. Oh my gosh, I have so many tabs. A bunch of different interesting plots to look at the different types of sets of planets that are out there, as well as subsets for like the Kepler mission, which is another transiting planet mission. Is looking toward the toward like one field of view to search for Earth-like exoplanets, whereas TESS is a full sky survey looking for exoplanets. All right, let's get into what that data that we just looked at plotted looks like in the database. So here we have kind of every solution of a published confirmed planet in all in one table. So that means there's multiple lines per planet if different measurements have been made by different research groups or authors, and maybe they've refined the measurements that were previously published or added new ones. So that's why this table says it has like 38,000 entries when there's a little less than 6,000 confirmed planets. All of these columns are kind of the default columns that NASA Exoplanet Archive kind of just like prints out, but there are a lot more that you can look into if you're interested in picking out other data for your needs, like whatever your use case is. There's like different IDs that you can query. Often, like a TIC ID or a Gaia ID is useful to like query a system within other databases. Um, there are also different discovery um, discovery method and detection method um, information. There are different units for the different kinds of orbital parameters. So I think it just has Earth mass for me, but oh wait, I guess it already printed it out. Anyway, if you are going through your tutorial and you need to find some information that's not already shown for you, this is where to look for it to print out. Just like add something and then press update, and then it'll add it for you like that. So yeah, this has all of our different orbital period, radius, mass measurements if they exist, eccentricities, equilibrium temperatures. It's not computed for like every system, depending on how they were able to study the system. There's a link to papers, which is pretty useful. So this will take you to discovery papers or the stellar, that was a stellar parameter reference paper, where you can learn about how they determined these values that are in the table. And same with the planetary, and they will kind of go through their research methods there. And some system parameters if you're needing to query, like if you're looking for the uh, coordinates, for example, to see if you can observe this with your telescope. find it there, and so on. Typically, when I use Exoplanet Archive data, though, I don't go to this database with all 35,000 individual solutions because you have a bunch of repeats and you're not sure which one you're supposed to accept, right? If you want to get, like, for example, the mass of 14 Her, there's like all these different masses and you're not sure which one you want. So there's actually the planetary systems composite data right here that has kind of like the either most current or most accepted solutions for each planet. So now we have one entry for each planet, one measurement for each planet, and this is for each of the 5926 planets that have been discovered so far. So typically we'll just download this and work from there instead of that larger database. But if you are interested in looking at the different solutions and how they changed or comparing different research methods and figuring out why their solutions are different, that is a great place to look. But yeah, it has kind of all the same information. You can select the same columns and look for different information that you're interested in here. You can also filter your table using these little arrows at the tops of your columns. So if you're interested in just looking at what are the smallest planets ever discovered so far? Oh, that's opposite. Okay, so the largest, I guess, is 77 times the size of the Earth. The smallest looks to be uh, zero point 0.3 for ones with radius measurements, of course. Not all of them do. You have some pretty small mass planets too. Whoa, that's tiny. Anyway, so you can filter by this and look around on your online like portal if you're interested in like filtering and looking at different types of planets that way. You could also like type in specific values, such as a planet name, to look for a system that you're interested in. So I'm gonna look for 6324, which is a planet that I discovered. Can click on its name, the hyperlinked name right there. It'll take us to an overview of the system if my internet worked. So each planet has this kind of like overview, or each planetary system rather. So for multi-planet systems, they'll kind of have a layout of the different planets in the system as well. Um, and it'll give you again like a table of kind of like the key system parameters, like planetary parameters, uh, uh, references where this system has shown up before, um, stellar parameters as well, and you could also link to the paper that way if you're interested in reading. Um, okay, I think that's kind of the usefulness of that main data table. There are all these other like lists of different types of planets and like candidate lists and different survey like subsets of confirmed planets from different surveys. But this is the one that's going to hold everything that you're interested in. Oops, I didn't mean to do that. Um, so I think I'll go. Oh, did someone raise their hand? Sorry, I was not looking. Go ahead.
I was just wondering, so when you click select columns over there, that's how you can filter what information is showing you, yeah?
Yes.
Okay.
Yeah. Yeah. So if you're like missing something, if you're interested in like transit duration in hours, I guess it's not showing that already. You just press update and now it'll show. Sorry, my internet's not great. Yeah, transit duration in hours is there now. Any other questions before I move on to our tutorial?
So Rena, there's a one question about the format of the data that you can download
Oh,
and go through that.
oh, right. Okay. So yeah, I think I just hovered over this for a second. That's a good question. So there are all these different types of formats that you can download. Typically, we work with CSV. I think that's the most simple um, format to download because we are learning with how to manage data with pandas. So there's just a read CSV function in pandas for that. But there's all these other formats as well. VO table, sort of Saffron Virtual Observatory. These are all other like I think kind of plain text formats where like if you have like some code that will parse these like data formats, like that'll be fine. But I actually don't know off the top of my head like how to use IPAC and VO tables. And TSVs are also pretty easy. You can also just use that in Pandas as well. You can download every column possible. I usually only download the check columns, but if you don't if you're not sure what columns you want, you can download all columns, which is everything on here. Oops. And you can also filter for different rows. You can select like a subset of planets that you're interested in, or you could just download all of them, which is typically what you do. And then click download table, and that will save to your downloads. And then you will probably want to, or you can save it to your downloads, or you can move it to whatever directory where you work on your research. So wherever you're going to store your Jupyter notebook when you download that too. Okay, that was a great question. Does anyone else have questions before I move on? Okay, if not, I will gonna pull up. So this will be available to you guys to work on your own. It's kind of practice for you to go through the online database and kind of do a little scavenger hunt and make sure you understand how to find information for a typical system or a particular system. Um, find papers, find references, read those papers, things like that. And the code part starts here. So I'm sure you guys have seen this once at least. It is just like the first cell of our code where we're loading in necessary packages or libraries. OS is just a file handling um, operating system thing. There's pandas for work with data tables, which we'll be doing as we downloaded a big data table. Matplotlib for plotting some data, and NumPy for numerical operations. And this kind of percent sign is a magic command um, where we're asking the notebook to display our plots in line. So I'll go ahead and run that. And so I've coded out for you kind of how to locate the data that you will have downloaded from Exoplanet Archive for this assignment. Um, I, as you can kind of see from my very messy directory, I'm not very good at making data directories. I kind of just shove everything in together, but I don't recommend doing that. You should have a data directory, so you should type in your string here of wherever your data is located, the file name. Yours will be slightly different than mine because I downloaded mine yesterday. And then you define this kind of overall path to your data. Ask pandas to read that path, and then go print out your data table. So this looks pretty similar to what we're looking at online. It won't show every single column. It just kind of like condenses it down. So if you're interested in seeing again what kind of data you have available to you, sorry, hold on. Arav, do you want to ask your question real
Uh,
quick?
Hello. Should we be seeing a code window here?
That's what I was going to
Because
ask.
we
Oh,
can still see
oh
the exam.
no.
Yeah.
Okay, hold on. Let me, I thought it was sharing my whole desktop, sorry. thank you so much. Sorry about that, guys. Yeah, so we're seeing the notebook that will be sent out to everyone. So I'm not going to go over this again, but yeah, this is just us importing our libraries and reading in our data. You will need to replace this uh, dear directory with wherever you save your data that you download from Exoplanet Archive, and you'll probably need to update this name as well because it's like dated. So I downloaded mine yesterday, but yours maybe will be downloaded today and will be a little different. So this is again the data table, the same, almost the same one that we're looking at online. You can do df.columns to find out what columns are available in the data frame that you just defined. And you can further out to that if you're not sure what column you need to index to do your plotting or analyses. Within the CSV file itself, sorry if, oh my God, I need to hide this. Like, there it is. Okay. Within the CSV file itself, there's a bunch of comments here. That's why we do comment equals pound. So it's not reading those lines as like table entries. It's just going to start at the first line where there's no pounds, which is here. But all of these comments give us descriptions of each column. So if you're not sure what PLB mass J is, you can look right here, but that's just the mass in Jupiter masses. Can confirm that this is the list of confirmed planets. Yep, that's matching what we see online. You can look up different information about the exoplanets in this table, such as how many just different discovery facilities are there? It says 72. You can look at different discovery methods or for things like that by using this like .unique function. So I recommend just kind of like practicing writing some of this code out, getting a feel for what different types of uh, different types of systems are in there. You can filter by host name, like you can look at for unique host names to figure out how many individual planetary systems are out there and not individual planets, because a lot of these are in the same systems. And then once you're done with that, we can get to some plotting. So I have like coded up some examples of how to do this, but I think in your guys's notebooks, there won't be all this code right now for you. There'll be some examples, and you'll need to figure some of it out yourself later. But you can refer back to this recording if you get confused. So yeah, we're recreating one of those plots that we looked at on Exoplanet Archive, the mass period distribution. We're just setting up a figure, plotting the necessary columns from the data frame here, adding some design specifications. You can change all these around and you can look up the documentation for this scatter function to see what else you can customize about it. I set the axes to log to make it more visible, because if you don't do that, oops. If you don't do that, it kind of looks like that, and that's not very informative. So as you go through these exercises, keep that in mind of like how you can design your plots to be more informative visually. And you, of course, label your axes. You can add titles if you want. But yeah, this doesn't look exactly like what we saw online, right? It doesn't tell us like what different types of planets were discovered by different methods. It doesn't really give us a feel for the differences in those detection methods, which was really informative. So we can add that in by filter or not filtering, but specifying the different discovery methods, which is also a column in the data table. So I just set up the table the same way as above. These are the same lines, just for like the kind of overall setup of the figure. And then we can filter, or we can define our discovery methods. This pd.factorize assigns a numeric code for each unique discovery method in that list. So for all the radial velocities will be like 0, for example, and then all of the transits will be 1s. And we do that so that we can assign like a color value. So we find a color map, which is just one of the default color maps in Matplotlib. There are a bunch of different ones. It doesn't have to be this tab 10. And the colors were normally the normal colors over the color map like this like DM array, and assigning the colors that way using C, the C. Sorry, what was it? Anyway, we then want to add a legend, right, to see what we're looking at. So it's not just some colored points. We need to know what we're looking at. So we can define the legend elements separately using that same normalized color codes for the discovery methods, and then plotting the legend like that. And now that gives us kind of the same plot as was on the line with the different discovery methods denoted by color. Maybe we'd want to change the alpha values a bit so you can see better, because it's just like very dense population planets here that we can't really see through. So alpha, which is for transparency, you can kind of change that to see, you can see the other planets better. Yeah, kind of. So I'll have you guys recreate another plot that was generated on a NASA Exoplanet Archive here. You can follow these examples to do the same. Just whichever one you're interested in. How much time? Oh, it's already 8:30. Should I leave time for questions, Faye?
Yeah, let's do it.
Okay, yeah. You guys can go through the rest of the tutorial on your own. A lot of this code will be in there already for you. And then there will be some places where you have to do code on your own, but hopefully it's pretty straightforward. Okay, I lost my meeting controls. Okay, Mohammed, you have a question?
Yes, I have one. In determining the path of the file, I used Google Colab and I used a syntax
Oh,
called upload.file so that I can choose the location of the file without the need to type or the path location. I can just use my
okay.
browser directly. So is it okay?
Yeah. If you're using Colab, for sure, you can, this will be different. You'll have to like, yeah, in your browser, or if you save it to your drive, you can like mount to drive. Whatever you need to do to like find your data file. Avi?
So this is all in the GitHub, or
Yeah, will be uploaded to
Yes.
GitHub after today's session.
okay, good to know.
Okay, if there's nothing, oh, Yuvraj?
Yes. So is this all made using AstroPy? I'm actually rookie in Python, so I don't know much about it.
Is what created using AstroPy, like the notebook?
Yes, the notebook. Is this created using
Um,
AstroPy?
no. So it uses a few different libraries, which are listed up here: Pandas, Matplotlib, and NumPy, mostly. I
Okay.
think I did actually end up adding AstroPy in later, for a units thing. You can do like AstroPy.units. But yeah, there's a mix of a bunch of different, uh, yeah, libraries. Anybody else? Okay, I'll hand it off to.
There's some
Oh,
more.
there's a
So one
in the
thing,
chat.
Rena, maybe you can quickly say.
Uh,
How can we use the Exoplanet Archive for research? Population level study, things like that.
yeah. So I guess for research, sorry, is that a new hand raised? I guess the way I use Exoplanet Archive for research is to search for candidates sometimes, or for looking at kind of a subset of exoplanets to compare it with something that I'm looking at. So I study Earth-sized planets. So you can like kind of filter for Earth-sized planets within the discovered planets um, database, and plot them against your own and see if what you're discovering is similar or different, and draw trends out of those planets that you're looking at. So that's kind of what I was doing a little bit of here in this notebook. We were going to look at tests or transiting planets and what those look like, kind of distribution of those, um, distribution of planets by radius. This like bimodality here called the radius valley is like a real feature where we're seeing like a dearth of exoplanets in this range. This was a huge research result out of the IFA a few years ago. So yeah, kind of like looking at the demographics of planets and looking at these distributions kind of helps us draw conclusions about how the planets form or evolve. So yeah, this was literally just like a histogram that someone made a few years ago that ended up being a really interesting result. And then yeah, you can take a subset of these planets, for example, the Earth-sized planets or things smaller than the Earth, look at their mass versus period distributions or mass versus radius, things like that. Model the trends within those, etc. Do we have more questions? Oh, I see the chat.
So Dean, you have a question?
Yes, so like I was just wondering if the data that the website has shown, so like is the data enough to find what is inside a planet, like what kind of does it have water or anything, or do we need some other techniques to find out that?
So you will want to do some more advanced modeling to figure out like what kind of interior or exterior the planet has. But from the mass and radius alone, you can compute a bulk density, just mass over volume, and compare that with the Earth and try to kind of draw out like a very, very high level conclusion about the makeup of the planet. Um, One
And
way to also look at that is to plot mass versus radius and then some composition curves along that, and see where the planets fall in relation to those composition curves. So there's like, I don't have an example of that open at
didn't
the
the table
moment.
also show metallicity, right? Or
Yeah, metallicity. But that won't really tell you if there's like water present at the planet. Um, But yeah, some more advanced modeling is required to draw like, is this a water world or not? But you can also, as we looked at earlier, click on the papers that discover them, and maybe they will say some things about the planet compositions. They typically will, because that's what we're interested in. I think I did have you do yeah, I had you plot radius versus density here, compute density, and then plot it. So that'll be an exercise for you guys to do on your own.
Hey, Rena, maybe we should wrap up
Yeah,
here. Thank you so much.
yeah. Yeah, thank you all. Great questions.